Hi, everybody. Thanks for coming to our first seminar of the semester. We're happy to have Satish back in the department to give this talk. Our next one is 2 weeks from now, and it'll be someone from the Humphrey School talking about racial disparities after disasters. So that should be interesting, and it's totally local data to the Twin Cities. But for now, Satish, we're going to hear about base flows.
Yes.
Thank you.
We go, or is a zoom on?
Zoom is on.
All right.
We're ready.
Okay.
I'll be here for any anything that comes up.
Yeah, I'm sure there's going to be something. I think this technology is too new for me. I've only retired 3 years ago. Well, I appreciate you guys coming over here, and I thank you, Anna, for getting a slot for me to give the presentation. I made a similar presentation last year in the water resources, not on this subject, but on something different. The title of my talk is Precipitation and Landform as the Primary Drivers of River Base Flow. There are two reasons for doing it, because we have done a lot of calculations and we're writing the manuscript. I need a feedback from you guys where I'm making mistakes. And the other is, many of you guys know, when you guys give a seminar, I'm always asking you a question, and John has sometimes said you ask hard questions. So get ready, and you guys ask me hard questions. So you will have opportunity to ask me questions too. It's a collaborative work. When you get in pandemics, we can't do anything. That's what you do at home, try to do some calculations. And this is a collaborative work with Dr. Carrie Wolf, who got a PhD in Denmark, and Dr. Andrew Kessler, who got a PhD over here. What do I do to move the slides? When I do, I cannot do this. Okay.
You can do this
Yeah, that's what
or click on the.
Okay, I'll do this one.
Okay.
Okay. So basically, if you're looking at, can we show the top part of the slide?
Yeah.
It's the first seminar, so we're going to have a little. Yeah, that's good.
Okay.
All right. So we are going to be looking at the differences in infiltration. Everybody knows when infiltration is. And we are going to be comparing infiltration in two different landscapes. One is the Des Moines Lobe, which is relatively flat, has a lot of depressions. So when it rains, there's going to be more water going through that landscape, and that's going to be more infiltration, and that's going to turn into more base flow. And the other is the southern Iowa drift plain, and I'll show you where they are, and other landforms, and they are steep soils, steep landscape. So when you have rain, much is going to be lost as an overland flow or runoff, and there will be less water going through that landscape. So if you look at the first equation, which is the precip is equal to infiltration plus overland flow. Okay, that's a water balance. There's nothing unique about it. And so if you have a lot more precip, and you're going to have a lot more overland flow and a lot more infiltration going on. And if you look at the infiltration, that's equal to evapotranspiration plus a change in the water storage in the soil. Initially, you have some water. At the end of a period, you have another water, whether you increase or decrease, and that's going to add that. And plus the base flow. So as the infiltration increases, you're going to have also increase in base flow because the ET is relatively constant. It's not changing a whole lot within, except for 50 millimeters. Okay. So this is how the Des Moines Lobe looks like. Minnesota River Basin is a Des Moines Lobe. A lot of depressions. And most of these depressions are connected. Okay. So if you look at these depressions, one fills up, goes to the another one. This is a very young landscape, 14,000 years old. And so all the flow paths are not developed for going to the water, taking this water to the ditches or the river. It's only around close to the ditches that some of the water goes. So these are also called fill and spill. One fills up, goes to the next one, or fill and merge. So in this landscape, when you have a lot of water, a lot of depressions, there's going to be more infiltration. And that's what the Des Moines Lobe is. And this is the southern Iowa drift plain. It's a very old landscape. Top is lush, and underneath is Aeolian drift plain, which is a couple 100,000 or more years old. And in here, the pathways are already kind of developed over here. So if you look over here, these pathways have been developing. There has been erosion going on, and the water can easily go to the rivers. Also, because of this steep land, there are a lot of conservation practices they have put in, contours and other stuff, and try to cut down the soil erosion. Soil erosion is a big problem in these landforms. So now, before I go in the presentation, I want to tell you what's a base flow. Many of you probably have not taken the hydrology class. So if you look at this, we have a precip event. The yellow part is a base flow. Regularly, when the water is flowing in the river, there's no storm in the landscape. That water is mostly a base flow. And as you have rainfall event, the red part, then the hydrograph starts going up. This is the rising limb, goes to the peak and starts going down after some time and comes back to the same place as the base flow. Now this part here that you see is the recession limb. And this is kind of critical because if you know the properties of this recession limb, you can tell something about the soil properties. And we're going to be looking at that thing. So this yellow part that you see is a base flow. Okay, most of the time, this was used in the groundwater hydrology, but people have been using in the tile line because after a certain period, all the water that goes from the tile line, when the storm is gone, is mostly a base flow. So I'm going to be talking about two papers. They're both from Iowa. Somehow, when I look at these papers, they always publish in hydrologic processes. I always have some trouble with these papers. So this is by Dr. Basu, very well known, a good hydrologist. And she has published quite a bit, very good writer. And this must be a student of Basu. And then I'm going to talk about a paper by Keith Schilling and Matt Helmers. And both these papers look at the role of tile drainage on the flows. So let's look at what's the role of a drain tile. If many of you haven't seen these drain tiles, some of you may have not. It's a corrugated pipe with the holes in there. And if the soil above this tile is not saturated, water is not going to drip in that tile line. Okay, water has to be saturated. If you'll have a soil over here at the top, it has to be saturated before the water drips. This tile or any kind of tile is not a suction pump. It's not a vacuum pump. It doesn't take more water out. It's an interceptor. Water has to arrive over there before it can take the water out. And the arrival is very important because it's controlled by the soil properties. It's not controlled by any vacuum or anything. So tile does not increase the water flow or decrease the water flow. It changes the travel time to the river. And I'm going to show you how it changes the travel time. So here's a cross section of the tile line. So there is a tile in the middle over here, and these are the flow lines. So if you have a rainfall, water molecule that drops over here is going to travel directly over the tile, whereas water molecule that's here is going to follow some path like this. So we are going to calculate the travel time here and a travel time here. And we're going to also consider another situation where there's no tile line and the water has to travel all the way down to some distance to the river. So here are some properties of a Webster clay loam soil. It's a 43% saturated. That's the saturation water content. Yeah. It's a saturated water content, and V sub K sat is the saturated hydraulic conductivity in the vertical direction. And then you have L K sat, that is the saturated hydraulic conductivity in the lateral direction. So you have more like a some properties difference. So if you divide the conductivity, saturated conductivity by the water content, that's going to give you the pore water velocity. So the wetting front is moving at 1.27 centimeters per hour in the vertical direction and 1.79 in the horizontal direction. So here are those two situations. So we have two tiles. They are 24-meter spacing on the left, and then you have a no tile, which is a 30-meter deep going to the river. So the tile, how long it's going to take? It's 1 meter deep where the tiles are buried. So if you take the vertical pore water velocity or lateral pore water velocity, you can calculate the travel time. So the water molecule that's just above the tile is going to take 3.5 days in the table, or if it has to go halfway and come back through the flow line, it's going to take 31 days. Whereas in here, it's going to take 99.5 days. Most of the analysis, most people are doing it on an annual basis. So this time period is not more insignificant in terms of water contributing to the river. And even if you don't do it, sometimes people go over there in the field and say, we have a tile drain experiment and we have a non-tile drain experiment, put a bucket and measure and say, yeah, there's a lot more flow coming in. What they are not measuring is this part here, the water is still traveling. It's not reached over there. So you cannot ignore this water. It's going to eventually get to the groundwater or to the river. And most of the landscape I'm talking about, there's not much groundwater. It's a more localized groundwater. So the tile is mostly changing the travel time. It does not change the quantity. That's controlled by the water balance. So now that's a paper I'm going to be talking about quite a bit. Again, the title is Homogenization of Spatial Patterns of Hydrologic Response in Artificially Drained Agriculture Catchment. The main finding is the presence of artificial subsurface drainage leads to a homogenization of landscape hydrologic response. Basically, putting the tile line, you have homogenized the landscape hydrologic response. And that's not true, because most of the places where you have a tile line, it's a Des Moines Lobe. And there are a lot of depression. It's already homogenized because of the depression and it's a level. And that's what I'm going to show to you. So they use several different flow metrics. And the first is the base flow ratio, which is the ratio of the base flow over stream flow, daily discharge exceedance probabilities, recession coefficients, master recession curve, and then there are last one, two are the peak discharge and flashiness index. Because I was going over the 50-minute period that I had set, I had to take out the last two. But if I have the data, if somebody is interested afterwards. So this group, Dr. Basu's group, they used 24 watersheds in the state of Iowa. And this is the Des Moines Lobe, the brown part. This part here, the light green, is the southern Iowa drift plain. This is the northwest plain over here. These are the Iowan surface. This is the Paleozoic plateau. And there are a lot of sinkhole over here. It's very similar to southeast Minnesota. So in here and in here, there's a Turkey River over here and Makakita River over here. There's a Floyd River over here and West Fork Ditch. And in here, this is the Thompson River, and this is the Nodaway River, and the English River is over here. And we took 23 of their watershed and we combined it with 3 of our own, which is the redwood. This is the redwood, and then we have the cottonwood, and we have the Lasur River watershed. So going back to Dr. Basu's paper, they used 10 years of data from 1996 to 2005. And here they're plotting is the percent row crop versus percent tile. And they're saying is basically the tile drainage is mostly where the row crops are. And that's true. Most of the row crops are in the Des Moines Lobe, and that's where the tile drainage is. And in here, they're showing the catchment slope and the percent tile. And they are also saying the tiles are mostly in the level grounds and not where there's a steepness. And that's true too, because we don't need drainage on a steep soils. There's a natural drainage happening over there. So this is our data of the 26 watersheds. And I have plotted the stream flow over here versus precip. And if you look at stream flow over here, but when the precip comes, it's partitioned into ET, and there is some storage, and rest of the water goes to the stream flow. Okay, it's a water balance equation. So if previous year, let's say there were a lot of rain, several years there a lot of rain, then there's a lot more storage in the soil. And at the end of this period, you may still have a lot of water left, but not enough. So this term becomes plus, and so it's adding to the precip value. So previous year, wet year means you're going to have a lot more stream flow. And that's what all these points above the lines are. Previous years were wet years. Similarly, if S sub I, previous year storage was less because of dry soils, then some of the water is going to stay in this profile, and that's going to become a P is going to be less, contributing to the stream flow, and those are the points underneath. Now I'm going to take the points out and I'm just going to look at the only lines. So there's some difference. Some of the difference that you see at the higher end is because we're fitting an exponential function, and exponential function has a tendency to give more weights to the end of the curve. But also, this is showing some difference in the growing season. So the top parts are the northern part of the watershed area that we're talking about. These are the southern because we have a longer growing season in the south than we have at the in the north, and so there is a lot more evapotranspiration going on. But all of these curves are nearly similar. Okay, they're kind of coalesced into it's following the water balance approach, and we have published this thing before, and there's nothing new about it except for when you look at these pink line, and there's another one which is a green line. And when you take the precept to 0, it never goes back to 0 as a stream flow. It should go to 0. And what it's doing is in the southeast Minnesota, where you have steep landscape, limestone bedrock, there are also a lot of disappearing and appearing stream flows over there underneath. And you're looking at physically at the top what the boundaries are, but the boundaries are much bigger. So it's bringing in the water from the outside and contributing to the stream flow. So here is the base flow. You can separate it out using the hydrographs and see how much was the base flow in a given year. And this data goes back to 1920 to 2009 or 1940 to 2011, both the stream flow and the base flow. And again, you'll see that infiltration. Base flow is infiltration. This is the water went into the soil minus the ET and then some storage. And again, previous years were wet, then you're going to get points on the top. And if previous years were dry, then it's going to be points at the bottom. So if I take the points out, you got a lot of variation among those curves. It's not like compact like a stream flow. So that variation is because of our landforms. Okay. And now if you take this data, and again, you can see this pink and there is green one over here. They are high over here and low over here. And I'll explain that to you guys in a minute. So now we are going to separate it out, all these curves by the landform. Look at the Des Moines Lobe. This includes 3 Minnesota River and then 7 or 8 of the Iowa rivers. Because of the depressions, because of the level ground, the base infiltration is high and it's going through it, and base flow is about same. This is the southern Iowa drift plains. And again, you'll see some difference over here. And these are the Northwest Plain rivers. These are the Paleozoic plateaus, and where you have sinkholes and appearing and disappearing rivers underneath. And they are contributing to that flow, base flow in the system. So now going back to Dr. Basu's paper again, the first matrix they used was the base flow ratio. What proportion of the stream flow is because of base flow? And you plot over here the base flow ratio versus the catchment size. And you'll see all these blue points over here, they're greater than 50% tile line in those watershed, and the red are the less than 10%. So they are arguing that, look, this is almost flat. So this is where all the tile lines are, and they have homogenized it. And this over here, they're less tile line, and they are a big difference over here, but at least at lower, smaller catchments. Above a certain level, they're saying catchments are becoming kind of similar. And in here, they've shown, again, the same data, base flow ratio versus the catchment tile. It doesn't matter. This tile, most of the tile watersheds are in the Des Moines Lobe. They are not because they're tiled and that's becoming constant. And I'll show you that in a minute. So let's see why both of them kind of converge above a certain catchment area. It doesn't matter which side, whether you have tile line or which plane you have. Think about this watershed, which is the Minnesota River watershed, and you're measuring the flow over here at Jordan. Okay, it's 17,000 kilometers square, and now you have a small watershed like here, which is a redwood watershed. Now let's assume there's a lot of rain in the redwood watershed. Okay, so you can measure the stream flow, you can measure the base flow, and you'll measure the storm flow. So there's an overland flow and there's a base flow. And if you go over here at Jordan, that storm flow that you measured is going to be really a ripple. It may not show up as a storm flow because it's in a smaller watershed. So in a smaller watershed, you can see the differences. It doesn't matter what the landforms are, but on a larger watershed, irrespective of the landform, they're all going to look alike. And that's what they're finding in their analysis. So now I want to put those base flow ratios by landform. So what you saw, the base flow ratio, now I'm putting this as a function of time. They were doing only 10 years of analysis. So all their analysis right around here. And these go back to 1940 over here. This goes back to 1921. So if you look at these values, they go from about 0.55 to 0.8 or 0.75. In this case, most of the little ones, they are around 0.3, and they start at 0.3 or 0.4 and start going up. There's a sharp increase over here in three of those watersheds. And this is in the Northwest Plain, and again, very sharp increase. Whereas almost each of the watersheds, irrespective of the landform, there's a slight increase over time, okay? And that increase is because our climate signal has changed. So here, I have taken the data. These are the daily precepts that you see over here from 1938 to 73 and 74 to 2009. They're about 36 years each. And this is for Clarinda, Iowa, which is the Nodaway watershed. Here is the Webster City Boone River. This is 7 percentile. This is 81 percentile. And these are the bins that I created, 0 to 6 millimeter, about 1/4 of an inch, 6 to 12, 12 to 18, and so on. And these are the number of days in those 36 years that the precept was 6 millimeter or 6 to 12 meter and so on. Now, if you compare these two values, there are a lot more events which are smaller. These are smaller size events. And there are a lot more events in the recent period than it was in the previous period. So if you have small events, what happens? Most of that water is going to infiltrate, and that's going to increase the base flow. So in recent year, we are seeing more base flow because of more infiltration, because we're not only getting the total amount is higher, the big events are there, but small and medium-sized events are increasing too. So if you look over here at the bottom, we got 98 feet of water in this period, and that's before the tile lines happened. This is 107, and so additionally, we have been getting 8 and 8.8 feet of water in rain that either went as runoff or went through the soil. So some of that water went through the soil and increased the infiltration. In case of Des Moines Lobe, it's much higher because of the depression areas, and all the climate is very different. So this slight variation you saw in the base flow increase over time is because of the climate variation. The one thing I have not done in this one, these are individual given day values. So I'm assuming they're independent. So what happens if there was previously a very high event and then next day was small, it's going to be counted as small. And so there's some interaction, and that might be overland. So I think that's the analysis that somebody needs to figure it out. It gets pretty complicated when you think about this probability of this compared to the probability of that, and so on. Now let's go back to those 3 watersheds in the southern Iowa plain, and then you have 2 in the northwest Iowa plain. That's where there was a drastic increase in the base flow, starting from around 0.3 and becoming 0.7 or 0.5 or 0.6. So these higher values in recent period is suggesting that we are adding some more water in that landscape. Okay, where is that water coming from? That means there is a more proportion of base flow than the stream flow. So this is the conservation practices they have implemented in those watersheds. So again, the first 3 are the southern Iowa plain. These are the northwestern Iowa plains over here. And the conservation practices are pond and dams, backslope terraces, water and sediment control basins, contour buffer, grass waterways, and strip cropping. The red colored numbers are what you want to concentrate on. These, at least the 3 one I know, they're mostly animal agriculture. They don't have enough groundwater, and they are using the water that they collect through ponds and dams for drinking purposes of the animals, okay? So if you have 3,000 ponds or 9,000 ponds, you're holding that water, it's controlling the soil erosion, so you're increasing the infiltration. These terraces are back slope terraces. That means they go back and there's a vertical inlet which has holes in there, and the water stays there for 3 to 4 days and going to be more infiltration. And then these water and sediment control basins hold the water, hold the sediment. Again, there's a pipe with a hole right in the field. That's increasing the infiltration. And that's why in recent years, we are seeing much higher base flow over stream flow than we used to have previously. So let's look at the second flow matrix, which is a discharge exceedance probability. So here, what they have plotted is a daily discharge versus the probabilities. Basically, it says is 1 out of 100 years, you're going to get this kind of discharge in these watersheds. They have 7 heavily tiled watershed and 7 not heavily tiled, less than 10%, more than 50%. So they're saying, look over here, these probabilities. There's a lot more variation over here and there's less variation over here. So we must have homogenized the landscape. And again, they are using 10 years of data, okay? And that's again not true. This variation I'll show you is because they're assuming, even though it's a 10 years of data, there's almost all kind of watersheds have the same coefficient of variation in the climate. And that's not true. So this is the same watershed they have plotted over there. Heavily tiled, it's in the Des Moines Lobe. These are in other landforms. And these are the average precept and the standard deviation. Look at the coefficient of variation. There is a much higher coefficient of variation in the southern Iowa drift than it's in the Des Moines Lobe. So Des Moines Lobe, all the watersheds were compressed because of that reason. Let's go to the one more step. And so we picked again the 2 watersheds and calculated the probabilities, discharge exceedance probabilities. So one is 80% Boone River, and that's a notable 7% tile line. So we are using the data from 46 to 2005 and 37 to 2005. No, for each watershed, we are taking every 10 years and we are calculating that line that they did. No, it's the opposite. Tile drainage, less tile drain has less variability, and these heavily tiled drainage has more variability. So what they were looking at is the variability because of the climate. They were assuming all the watersheds have similar climate because they used 10 years of data. And it's not because they have put tile line in there and the exceedance probabilities are more compressed. The next flow matrix that they're using is the recession index. Again, recession index is a flow, is the rate at which stream flow declines after a sufficient time has elapsed since the last discharge recharge event. So basically what you're doing is you're looking at the hydrograph. Again, this is the gauge height, or you can plot the stream flow. This is the base flow over here. We have a rain event. We have a rising limb of the hydrograph, goes to the peak and starts coming down. And we're going to see how long it takes when this limb approaches the base flow. And we're looking at the slope of this line. That's basically what we're doing. How many days it takes? So they're looking at different methods and we have used it. We use the USGS method. They have calculated their own. Let's look at the recession coefficient. That is the slope that they're making versus the catchment size. And again, 50% and 10%. And again, they're saying less tiled areas have higher recession coefficient than you have the one which are greater tiled. And again, all these irrespective of size, they're kind of uniform. And that's based on that. Again, they are saying it's homogenize the landscape. That's not true. So again, they have calculated the recession coefficient over 12 months period, going back to January through December. So we did the same thing, and we have 6 watersheds over here, and they're in the Des Moines Lobe, Southern Iowa Drift, Northwest Plain, and East Central Iowa Drift. So we are dividing. They should not be comparing 2 different watersheds with the 2 different landforms. They should be comparing the same watershed with a 2 different period before and after tiling. So we divide our data from 1941, in this case, to 75 before tiling, and this is 76 to 2011 after tiling. So if any tiling effect is there, it should show up in here. We know there's some change in the precept, but even then these differences are very small, about 3 or so. This is in the Des Moines Lobe, these two, the Redwood River in Minnesota, English and Lobe is in the Southern Plain, which are non-tiled or less tiled. Again, you find the same difference, 31 to 28, 32 to 36, 38 to 32 to 36. Now, Floyd River is the one that has been giving us problem. It's very high difference. We don't know, again, this watershed has very low tile drainage, okay? This is not a steep soil. And then Makakita is in the eastern part, and that's about the same. But our January through December period, tiles are not always running. So if you're looking for a tile line, we should not be using the whole year, because in February, there's hardly any river flow. Or in November and December, there might be less flow. So we said we're going to look at the 3 months period. April, May, and June, that's when we have the tile lines, and you'll find the same kind of behavior. The 21 is the top one, if I can get this mouse to 21 and 26, and 25 to 31, 27 to 29. The difference is irrespective, whether you have a tile line or no tile line, the recession coefficients are same. So it doesn't matter. It has nothing to do with the tile line. This is the before tiling, and this is after tiling, intensive tiling. Around 1975, when the farmers started putting the plastic tile line. The one thing that's very important is this variability. These are the ranges, goes to 10 to 60, because there's so many recession limbs over the period that we're working with, the slopes are going to be different. So this is again the same thing that you're finding. So the next parameter they used was a Master Recession Curve, which tells us something about the properties, whether they have changed because of the tile. So how do you put it together? You guys saw the recession coefficients. So in here is the discharge on the log scale, and here is the time. So you had an event, let's say you are looking at 10 years of data. So you had a peak discharge and then slowly coming down. You have another event, peak discharge and slowly coming down. The recession coefficients for the slope of those lines. Now you take all those events and put it together, okay? And arrange them in a descending order. And all the time when the base flow comes together is your Master Recession Curve. Now has that curve changed? That means the properties have changed. That tile might have some effect on the properties, but that's not the case, because water has to come to the tile line to be intercepted, and above properties of the soil are controlling it. So they did not give the Master Recession Curves, but they said, we are going to plot the R value, the coefficient of determination, try to see what's the best fit as a function of the catchment, again, 50% and 10%. So now you again see over here, these values are much higher, these values are low, but again, all of them are 0.8 and 0.9. That's a fairly good fit. The fit is in the previous diagram that you saw over there, that you are fitting a recession, and what's the R value for this line. That's basically what they're doing. So in here, you'll see that, again, whether they use the exponential function or power function, it didn't make any difference. So what we did is we said, we are going to look at the Master Recession Curves for each of these 6 watersheds that we did. And again, we're looking at the period 1941, before extensive tiling, and afterwards. Boone River, this in Des Moines Lobe, we are not finding much difference, okay? This is a 3-month, April, May, and June. These are January through December. And this is the Redwood. Again, some differences, but not extensive. The same kind of differences you find in Southern Iowa drift plains, where there's hardly any tile, okay? So you're finding the same kind of differences. Now in here, Makakita, you're finding similar differences in the eastern part of the state of Iowa. The only one that's giving us is this Floyd River. And we think it's because of the climate, but we don't know what other things they might have done to increase the water infiltration in those watersheds, and thus cause more base flow. That takes me to the second paper by Keith Schilling. Many of you know Keith, and Matt Helmer too, probably you have known about him. They both are good scientists. Keith has published quite a bit. I did not agree with most of the stuff that Keith has done. So we published and they kind of commented on our paper and we replied. And so that's been going on. And basically what they're doing is they are simulating water flow, stream flow using a Drainmont model, and they're calculating the Master Recession Curve. So this is the Master Recession Curve as a function of the log of Q versus time. And these curves are Master Recession Curves. And the Drainmont, their simulation they're doing is there's a 24-meter spacing or there's no drains, just like what I did initially in the presentation, okay? And they're saying if you look at this, it has changed the properties of the soil or the landscape. Now, I've shown you this graph, and just I want to point it out. Des Moines Lobe always have around 6 and 7, okay? 0.6, 60% to 70% of the stream flow is a base flow. In here, mostly it's around 30%, okay? These other ones that you saw was because of the conservation practices. So keep those 0.3 and 0.6 in your mind or 0.7 in your mind. This is the Drainmont simulation they have given. So they used 7 years of data and they predicted that stream flow. And then they looked at the base flow, okay? Average stream flow was 208 millimeter for 24 meter spacing. And in here, the flow is 201 millimeter, which is not very different. It's kind of similar. So it goes back to the water balance equation. Stream flow doesn't change for a given ET values, okay? Now looking at the base flow is 3 times higher. So if you do the calculation, have the base flow ratio, which is the QB, base flow over stream flow, we are going to get a 70% of the stream is coming as a base flow. Whereas here, we are going to get 25% of the stream is a base flow. And that's not right. Because in a Des Moines Lobe, you should have the same amount of base flow. You guys saw that 0.7, 0.6. 20.25 or 0.3 refers to southern Iowa drift plains. So they are comparing, even though they're simulating the same soil, same climate, it's a problem with the Drainmont. Now, most of the models are one-dimensional. Drainmont is a point model, just like not AgNaps, HSPF, or other models of SWOT model and other models people have used. So you got a point over here, rain is coming, whatever infiltration happens, there is a runoff. The runoff, you assume, directly goes to the river. But you saw in the Des Moines Lobe that does not go to the river. So here is a storm flow that we have calculated. So over here, we have 58 millimeter of overland flow. Look over here, it's a double the amount. So to compare this for the Des Moines Lobe with and without tile, they got to have the same base flow and the same storm flow. Because in here, when you're simulating, let's say you're simulating Drainmont at this point, there's going to be some infiltration and the excess becomes the runoff or the storm flow. And they are assuming this water has already gone. This water has already gone to the river, whereas a lot of depression, it goes over here, it probably will never get out of it if it's far away from the ditch or the river. So they are not simulating the correct simulation between a no tile and a tile condition for the Des Moines Lobe, where most of the tiles are, okay? Base flow is going to be similar. I've shown you those in those curves. So most of the model people are using their point models, their one-dimensional models. They do not simulate correctly the base flow in a no tile condition. They don't even simulate correctly most of the flow that they have been simulating for a Des Moines Lobe, because a lot of depression, they don't account for the depressions. And that's what it's a 3-dimensional problem, not a 1-dimensional flow problem. So what's the implication of all this? We had published a paper, Nathaniel Baumer, who did a master's over here in the department with me. And this was a diagram in his paper. This is the end yield versus precept. And we have plotted the Minnesota River and the Grand River. The Grand River is in Missouri at Sumner. It's a steep landscape, just like Thompson and other Nodaway River that I showed you. So this is the amount of nitrogen. If you multiply by 10, that's going to give you kilograms per hectare. Now we are getting, for a given precept level, we are getting a lot of nitrogen in the Minnesota River. It's not because they're putting a lot of nitrogen, because they have same kind of nitrogen. Their applications are similar. It's just because much of the water from the rain runs off as overland flow, so there's less infiltration and less base flow. So if we wanted to pull this line down over here, that even if we have higher precept, we want less nitrogen, we got to get the runoff out from that landscape. Don't let it go in the depression. And that's what farmers used to do. They had surface inlets. But then there is some sediment going and phosphorus going, and the MPCA and the Bowser, they didn't want it. So farmers like the tile line. So they put a tile in underneath. So there's a lot more drainage going on. So now this was based on, at that time, we had not looked at the base flow. Now we look back, I just showed you over the base flow, then these two curves should come together. So instead of plotting the precept, if you look at over here, it's a base flow. These curves are relatively similar. In here, you're getting a divergence because these are the upper points over here, and I showed you that exponential function tries to fit the endpoints of it. But that's what people got to do, look at it in terms of nitrogen yield. So the only way to cut it down, nitrogen, is you got to cut down the infiltration. Our wet climate is going to have more infiltration, and it's going to carry more nitrogen. And you don't want that, okay? So this is a way to compare it. You guys got to compare all the watersheds, and smaller watershed would be better. Make sure there is no input source from outside the watershed for the base flow. Some of the communities are getting the groundwater, use it and put it in the river. That's a base flow. You want to subtract that. And the reason for giving this seminar was not only make the presentation on the calculations we have done, the analysis we have done, also look at this Minnesota statute that the legislature passed last year. They gave $2 million to put water storage on the Des Moines Lobe. There's a lot of activism in Mankato area, even in the cities. Farmers are bad. They are causing all this problem, increase in flow because of tile line, causing the bank erosion problem, and so on and so on. And these are the 6 elements that the Bowser or somebody has come up with. It's the retention structures and basin, soil and substrate infiltration, and wetland restoration, creation, and enhancement. Those are the 3 that's concerning me in terms of the work we have done on infiltration and base flow. Because all of these elements, if you put more wetlands on the upland where farmers are putting nitrogen, it's going to increase more infiltration, more base flow, you're going to have more nitrogen going down. They are all right now, farmers have not changed the landform. By draining the wetlands, they have created enough storage. If there's a big storm, it can still hold the water. But the problem is, if you keep on putting the wetlands on the uplands, where the farmers have a water table, you're going to have more nitrogen losses, okay? So if you want to restore some wetlands over here, do along the river length. All of these things should be along the river length, so we don't have a change in the water table and creating more nitrogen loss. So they're trying to control the sediment, they think, and sediment is not because of the river flow. Many of these guys have been correlating the sediment loss or sediment concentration to the river discharge. It has nothing to do with the river discharge. There is seepage happening in those big tall banks, and they're slumping. And it doesn't happen along the river length, it also happens along the roads in that landscape. Because we are getting too much water, the soil is basically weak and is failing and coming down. So in conclusion, precipitation followed by landform are the primary drivers of base flow, okay? Tiles do not increase stream flow or the base flow. Tile is not a suction pump, it's an interceptor. Water has to get there before they can take the water out. And comparison of watershed from 2 different landforms to evaluate tile effect is a wrong approach. Last year, I gave a seminar in the water sources, and that was dealing with Sarah Kelly Belmont and Dr. Fufla's paper, where they compare the Chippewa River in Wisconsin, which is a very steep watershed, with the Minnesota River, which is a flat with the depressions. And they say there is no tile line over there and there's a tile line. It's because of tile line. That's not true. It's because of the level ground and the depressions. And the Des Moines Lobe, where the Minnesota River basin is, and where most of the nitrogen is coming in Iowa, is conducive to increase base flow, and thus nitrogen losses due to slow relief and presence of depression. It's a natural setting, okay? The only way, if you want to control nitrogen, just cut down, don't have any agriculture, okay? There's no other way of, at this 40% that the agencies have a goal, it's a nonsense goal. They'll never achieve it. That's the way the landscape is. And we got to be careful in putting the holding ponds. I showed you in those 3 watersheds where there are steep base flow ratios, what the many conservation practices have done. It has increased the base flow. So putting these holding ponds on the upland to increase infiltration, especially in flat landscape, is a bad idea, okay? These management practices will increase nitrogen loss to rivers, especially when we are getting 8 to 10 feet of additional water. We are going to get more nitrogen. So with that thing, I want to thank few people. We got a great help from Greg Sporden, Pete Boulay, and Kenny Blumenfeld. You guys know they are the DNR people downstairs. They have been very helpful to me for at least 10, 15 years, getting me the climate data. And Dr. Paul Barlow, he is with the USGS in out east. They used to have a part program, another program for calculating base flow standalone, but they put it together. And somebody who's old like me doesn't know the technologies. I needed his help, and he was very gracious in putting and helping us with the tutorial and toolbox. And then John Niebuhr is an excellent guy, excellent scientist. He and his major professor, Broussard, had published among the first few papers on the recession coefficients. So I had some initial discussions with John on the recession coefficient, and he was great help. And then Brad Miller is with the Iowa Soil Informatic lab over there, and they were very nice in sharing the shapefile for the picture that you guys saw on the landforms. So with that thing, this is the last slide. And this is a wet depression in the Minnesota River Basin near Lambert. This was taken by Dr. David Thoma, who got his degree over here. And you can see these depressions are not very deep, and they're going to hold water, and they are going to influence the groundwater, the shallow perch water, and that's the leading part of the nitrogen loss. So we got to be careful what we do on the uplands. So with that thing, I'm going to stop over here and open up the floor, if that's okay with Anna, and if you guys have questions.